Ray Laflamme, thank you so much for being here. It's great to see you.
You're welcome.
I want to start with a big question. How's life?
Life is really good. Definitely after a pandemic of 2 years, the life seems to kind of pick up again of seeing people. And then I think that pandemic has made us enjoy the kind of precious moment even more than we did before, realizing that uh, there are things that goes in different ways as life goes. And then you adapt to them, and then suddenly you realize kind of what are the diamonds that kind of before you were kind of neglecting.
Yeah. This is part of the reason I was so excited to talk to you. I've known you now. I did the math. I think it's been about 12 years since we first met because you hired me to work at the Institute for Quantum Computing in Waterloo, where you were the director. And I still remember the first thing you said to me on the first day of the job. I bet you don't remember this. I remember it clearly. I walked into your office. You said hello, and you said, "Lose the tie." Because I was wearing a tie, and I thought, "Oh, okay, I like this guy." And then you were such a mentor to me. I had come out of a journalism career, and I knew practically nothing about quantum computing and quantum information. So you showed me around this Institute for Quantum Computing. Could you tell our listeners what the Institute for Quantum Computing is, how you got involved, and what it's for?
Um, so the Institute for Quantum Computing is an institute at the University of Waterloo whose aim is to develop the science of quantum information, and quantum computing is a part of it. It should maybe kind of be called a little bit more generally, but it kind of names are names and they stay beyond. That includes quantum computing, quantum communication, quantum metrology or quantum sensors, and some materials that are essential to build devices that use quantum mechanics. So it's an institute whose first goal is to do the research, the basic research related to quantum information. The second one, to train a generation of students and scientists and engineers who think quantum.
Mm-hmm.
So we all kind of grow up and we are learning Newton's mechanics or classical mechanics, even if most people don't call it that way. That's the way we understand how to control our car by using our bicycle or whatever, flying in an airplane. But really, the world at its very kind of fundamental part behaves differently. Like atoms and molecules and electrons and protons have a different set of rules. And then we want to use these rules to manipulate information. That's the Institute for Quantum Computing.
Could you give us maybe an example of one or two of those uniquely quantum rules that you're trying to exploit, and why? Why harness these properties?
I'm happy you say why harness these instead of why do they behave that way, because we just don't know why they behave that way. The world is built in some way, and maybe there's a fundamental reason that one day we will discover that it cannot be otherwise. It had to be this way. But right now, we just kind of explore the world and try to understand how it works and not necessarily why it works that way. So one of these properties of quantum mechanics is called the superposition principle. In the physics of Newton, or what I call classical physics, we think of objects made of particles, and particles are little things that are at a given position in time and as at a given velocity. And this works very well to describe most of the world that we interact with in day to day, except people like me and my students and my colleagues who suddenly go in labs and isolate these particles very well and try to see how they work. And what we find is there's something called a superposition principle. These fundamental particles of nature can be at more than one place at a given time. So a single system can be here and there at the same time. And so we are trying to use this property, the superposition principle, and use it to compute. And so we kind of discovered that if we use these properties, we can build computers, or we are attempting to build these computers. We're still kind of early in that stage, although we have some really good prototypes that shows that the science is okay and kind of things are working the way that we're thinking that they should work. And so we found that by using the rules of quantum mechanics, the theory that described this kind of very small part, of the world. If we use the rules of quantum mechanics to compute, we can solve problems which seems to be intractable with classical computers. And suddenly it tells us that if we can do that, there's a wild world of information that will open to us that we haven't, which is totally surprising because it is mind-boggling what we've seen in the last 50 years with the computing or information revolution. Before people were having to jump on a horse to tell the story to somebody else in the 16th, 17th, 18th century. And suddenly people invented the telegraph where we can send things or kind of short waves to send messages. And this turned into computers in the 1970s and 80s and the cellular phone that we have today. And when we look at our kids, if you want to give them a hard time, you take the cell phone off, it's like the end of the world. Like they cannot connect. And they've learned, like you and me have grown up where we had neighbors and our friends were neighbors. Our kids grow up where their friends can be in France or in Japan or in South America. So instead of having a little local village, we have a global, the Earth is a global village, all putting this together. And that changed the way that people think, the way we behave, and what we think about the future. So this incredible change of how we conceive the world because of this information revolution. And suddenly quantum mechanics comes in and tells us things can be very, very different. We can manipulate even so much more information that these classical computers cannot do. So there it is. And this is what the Institute for Quantum Computing, and I would say the Parameter also, are investigating these pieces and try to put all of this together.
So as you've alluded to, this field and the related technology, it's really very quickly growing and changing. So I would assume that would mean the goals of a place like the Institute for Quantum Computing would also have to evolve. Can you tell us a little bit about how those goals have changed throughout the time that you've been there?
Yes. In fact, I'm kind of thinking of this and kind of putting myself back 20 years when I first came to Waterloo. And I said, at the time, the goal was mostly to convince people around that this idea of quantum computing was not totally crazy. And I say not totally crazy because we don't have them yet. And me as a scientist, you shouldn't kind of believe something until you see all the goods. We don't have a full-fledged quantum computer today. And until we have one, you should have a little skepticism. Although I really believe we will have one, but this is a belief and not a scientific data. And quite a distinction between the two. So in the 2000, a lot of the work of the director of the Institute was to convince people that this was really an important field. And we seem to have done a very good job because people now there's investment from government, industry, many universities across Canada and around the world have group of quantum information. So now this is different. Now a lot of the work is really to develop these ideas to, in part, better understand where the power of quantum computing comes in, find new class of algorithms that kind of quantum computing could help and kind of make more efficient, and then turn into how do we rebuild these devices and building them. So maybe 20 years ago, we were really asking, how can we really build these things? Now we have a bunch of blueprints and people are in lab trying to show them, and industry. It has been started, building quantum computers has become complex enough that it is hard to make this in a university, in part because it takes a long time to go from the first steps to the device that we have today. And generation of grad students are 3, 4, 5 years, and that's a little too short to kind of keep things going. So we can make proof of principle of certain mechanism or certain things, but it is really the IBM, Googles, and Xanadu, and those that are really kind of putting all the engineering together and kind of developing these ideas to get devices. And indeed, they are producing devices, not the one that we finally want, but enough to give us confidence that we are on the right track.
Takes a lot of pieces and a lot of collaboration, I guess.
Yes, a lot of pieces, a lot of collaboration, a lot of stamina, and a lot also of understanding where the problems and the challenges are and get over them and kind of moving forward.
You said that your primary job as director of the Institute for the first 10, 15 years or so was convincing people that this wasn't a crazy idea. Was there a time when you needed to be convinced that it wasn't a crazy idea? Were you a skeptic about quantum computing before you were a preacher about it?
Yes, my first piece of work on quantum computing was to try to prove that they would never work. And I failed.
You failed and succeeded, I'd say, in equal measure.
So after my PhD, I went to Vancouver and I worked with a physicist called Bill Unruh. And Bill is an incredibly good physicist. And he has this tendency he really likes to argue. And as a postdoctoral fellow, it turns out that sometimes it was very hard to work with him because every time I had a new idea, I would tell him black. And as a person who really likes to argue and sharpen your ideas, he would say white. And so I kind of would argue for black, and then he would kind of poke holes at my arguments, which after a while, it gets really tiring. Every time you have a new idea that you kind of get, it is really good scientifically to do this. But as a human being, being kind of trying to do research and try to make your name of kind of being pulled. So, but I learned that it was important. Many years after, probably 10 years after, I started to work on quantum computing. I went to a conference in Santa Fe. My mentor at Los Alamos National Lab, Wojciech Zurek, told me there was this conference on the physics of information. And I initially said, I don't want to go there because I don't know anything about the physics of information. And Wojciech told me, there's really neat people going there. And so, what is it? It'll take 2 days. And it was kind of 45 minutes away from Los Alamos. It was in Santa Fe. He says, just go. And so I said, okay, I'll go. And it turns out that was one of the very first time that, in fact, the first time I heard about this algorithm called the Shor's algorithm, which is crucial for quantum computing. It's related to factoring numbers, which are product of primes, using a quantum computer, which turns out to be an algorithm on which cryptography, in fact, most of today's world cryptography is based on the difficulty of factoring numbers, which are product of primes.
Cryptography being the stuff that keeps our information safe?
Absolutely. When you use your cell or your computer to log into your bank, the cryptography that is set up so that it is private is based, breaking that cryptography is equivalent of finding the factors of a number, which is product of prime. So I went there, and so this computer scientist, Umesh Vazirani, kind of explained this algorithm. And in fact, he started with a very funny story. Umesh is a really smart guy, he always has great ideas, all this. And he started this talk by saying, I haven't done anything interesting in the last 2 years. Which, saying, what? And usually scientists are not, all of them are not humble.
That was put politely.
So that was a little surprising to hear this. And he said, but I've heard about this algorithm called, which was going to be called Shor's algorithm. And he says, from this guy called Peter Shor, to factor numbers which are product of prime. And there was a buzz in the conference that this was really important and people were talking about it. At the time, I knew very little about cryptography, so it was very hard for me to really assess everything. But there was really a coherence in that conference. It was like for those who know physics, it was like Bose condensation of human beings' thoughts of kind of suddenly, wow, something's happening here. I came back to the lab and I started to think I was working on something which was called quantum decoherence. And I said, this quantum decoherence is going to be an obstacle to quantum computers, and I started to use little kind of toy or kind of simple models to show that if there would be quantum decoherence, quantum computers would not work. Mm-hmm. And so I kind of put things together. Not everything was tight and clean, but kind of I was pushing the idea that quantum computers would never work. And one day there is this thing called the archive where we get preprints for everybody around the world. I look at the archive and there's a paper by Bill and Rue on quantum decoherence and quantum computers giving exactly my message. So I was pretty miffed. And then I said, oh, it's pretty much the idea that I had. So, okay, my last couple of months of work, it kind of goes in the garbage. But then I said, no, Bill always asked me to argue white when somebody says black and the other way around. So I started to work to demolish his paper. And I tried to poke hole at it. And
which was essentially poking holes in your own ideas as well, right?
Absolutely.
So you wanted to demolish your own
Well, as a scientist, you have to look at both sides. Right. Like you don't know what the truth is. Mm-hmm. And we have ideas, and you never know if these ideas are right or wrong until you go through the whole details of the mathematical models and all of this. So I was poking the other way around to try to kind of demolish his idea. Then I didn't have to say to other people that I had the same idea. I can say, oh, this guy was wrong. So by doing this, I stumbled into quantum error correction. Mm-hmm. And so, which shows that not all errors will be kind of deadly for quantum computers. There's a family of models of errors that if they happen, there's ways to take care of them in a way. And at that time, many physicists thought that this would impossible.
Because decoherence causes too many errors and makes your computation worthless?
Yes. And quantum mechanics has this property. It's called unitary. That is, if you make a computation forward, if it is quantum mechanical, it should go backward also. And if noise comes in, naively, it seems that you cannot go backward again. Mm-hmm. So they would say, it's just not going to be possible to do this. And the idea at first level seemed to be okay, but if you start to think about it very carefully, it is not really correct. And this is what quantum error correction is really about, is to find a way to be able to go forward and backward in your quantum computation, even if noise comes in.
Mm-hmm. So you essentially demonstrated the opposite of what you thought, that quantum computing is possible.
Yes.
Amazing.
So I think we should have to, I should be a little bit more precise. It didn't show that quantum computation was possible because we don't have them yet, so we still don't know. It shows that noise and quantum decoherence are not a fundamental objection to get quantum computers. Mm-hmm.
And we also have to think about error correction in classical computers, right? So can you tell us a little bit about the difference, really, the fundamental differences between classical and quantum error correction?
Now that becomes a little bit more, could become a little bit more technical. So I'll try not to be too technical. But the idea is first related to the type of noise that we have. In classical computers, all the information is encoded in bits of information. Bits of information is the smallest unit of information that we have, typically encoded in a system with two levels. And we call them 0 or 1, like something which is either pointing up or pointing down, a little kind of magnetic moment, or a pulse of light which is there or not there, or a switch on or off. So all of the information is encoded in this. And the type of noise that we have is called a bit flip. So you have one bit, let's say you want to send it to me. If it is 0, we'd get 0, but suddenly there's noise between you and me. And then it gets flipped to 1 and I get the wrong answer. The idea of classical error correction is not to send your bit one by one, but to encode them so that instead of sending 0 or 1, you'll send me 0, 0, 0, or the 0, or 1, 1, 1, 3 bit, or the 1. And if one of them flips, then you can still recover the information just by taking the majority. If there's 2 errors, then it's going to fail, that process. But the process here will take care of the 1-bit error that comes in, which would not have been taken care of if you send it a single bit. So now you try to translate this for quantum computing, quantum system, and there were fundamental objections that this would happen. First, the noise in quantum mechanics is not discrete, like a 0 or 1, but it could look like continuous. The second one is that it seems that when we have taken the bit 0 and encoded it in 0, 0, 0, we've copied it twice. And quantum mechanics tells us that we cannot copy quantum information. And the last thing is that when we try to make this majority voting, then we have to measure the bits. And in quantum mechanics, if you measure it, once you measure it, and it's another property of quantum mechanics that I could have mentioned at the beginning of this podcast, when you measure it, then you kill the superposition of zeros and one. And so by doing this, then you kill the quantum information. So the question was how to get over this and these 3 objections. And the 3 ways now seems obvious once you know how it works, but it wasn't around the 1990s. And I'm not going to go into all details of how it happens, but maybe I'll mention one thing. So type of noise. It turns out that although the noise can be thought to be continuous, there's a way also of thinking it as being discrete. And the type of noise, quantum noise, is can be simplified to have either bit flips, the classical noise, or what is called a phase flip. So when we have superposition, there's something called a phase, and this phase gets changed from plus to minus. So we certainly have 2 types of discrete noise, and the combination of the 2 makes the type of noise that we have. So the continuous noise that we have can be thought of as a discrete piece, and then we can get over that first objection. And the last 2 are a little bit more complex, so I'm not going to mention exactly how they work, but there's a way to go through. So there is a theory of quantum error correction, and it turns out that classical error correction is like a subset of quantum error correction. It's quantum error correction when we don't have phase errors. We have only bit flip errors, and then in that case, things are a lot simpler.
And these considerations about noise and copying, they're challenges that you need to overcome when you're doing quantum error correction, but are they also kind of advantages when we're trying to encrypt data?
But the advantage is that you can keep these superpositions that we don't care in the classical world, because your bits are either 0 or 1. In quantum mechanics, and maybe I should have said this at the beginning of this podcast, that the bits in quantum information are called qubits, or quantum bits, and kind of a name coined by Ben Schumacher. And these quantum bits can be in a superposition of being in 0 and 1. So there's one way of kind of having a picture of this. You can take the surface of the sphere as the kind of quantum state that 1 qubit can have. The classical bits are the north and the south pole. We'll call them 0 and 1. But if you are anywhere else on the sphere, then you are in 0 and 1 at the same time. And so these different kind of states allows you to do something different. In fact, the transformation to go from 0 to a superposition of zeros and ones is something that is that classical computers cannot do. And so by having a quantum computer, suddenly you have different types of transformation you can do with your information. And the hope initially was to find shortcuts, that there would be shortcuts, that if you have different transformation, if you can do some things that your peer cannot do, maybe you can kind of find a shortcut to go somewhere else. And indeed, quantum mechanics and quantum algorithms are exactly this. They are a shortcut to get to the answer.
I remember that when you showed me around the Institute for Quantum Computing for the first time and showed me what the labs were, and then I would give tours to visitors around the labs. And so you would see in one lab, it would be all dark with lasers and mirrors, and you'd see these lasers bouncing off of things. And you go to the next lab, and there's a big nuclear magnetic resonance can. I don't know what you call it. This super cool. Your quantum computer prototype in one lab, and then another lab has ion traps. There's all these different approaches. Are they sort of different attempts to find the right way to do quantum computing, or are they all sort of part of the same effort at harnessing quantum information?
They're all different blueprints for quantum computers.
Mm-hmm.
And it's not clear yet which one is the winner in all of this. So people are making bets on which one will be the best one, and that's kind of different companies have different ideas of which one will end. They are indeed, they have what they have in common is that they all want to manipulate quantum information,
mm-hmm.
and they have different physical implementation of how to do this. And in some sense, we can think of in classical computers today, we have all chips. We all look the same. But if you do classical computing, you could have an abacus. An abacus is a way of manipulating information, and you can have a slide rule, which tells you how to calculate also. There are different ways of doing this. Now, I'm not going to compare the different implementation to the slide rule and today's kind of modern computer. Which one is the slide rule? Which one is the modern computer? I'm going to kind of say nothing about this exactly, but the different implementations are aiming to be the quantum computer. And maybe it's possible that there could be more than one that kind of works. Maybe one will work better for certain applications. Another one works better for some other type of things. Mm-hmm. And so investigating those right now are all kind of worthwhile endeavor to do. And there's also, I would say, a spin-off of having these different implementation, which relates to not necessarily quantum computing, but to quantum sensors. Mm-hmm. So quantum sensors are sensors which use, again, rules of quantum mechanics to better sense certain phenomena. They could be better sense the electric field. They could be better to sense the gravitational field. It could be better to field some different properties that we have around. And by studying either atoms or ions or light, then in that case, they can be more appropriate to certain places.
Right.
So an example of this is light. Like a fundamental difference between using light as a qubit and an atom as a qubit is that light goes at the speed of light. It doesn't stop. So you cannot take a photon and keep it here while you're doing something else on your qubit. They are going to move around. And so you have to find a way that if you want this photon to interact with that one, that even if this one goes around, that it has come back in the right state to kind of interact. Mm-hmm. With ion, it's easier because they are in a trap and they are there next to each other. Now, the difference is if you want to send information which is in an ion trap, quantum information, to your partner who's somewhere else, then you have to use light to be able to do this. Mm-hmm. So you can transfer information from the other. And that's pretty hard to transfer the information from one implementation to another one.
I remember you describing that in the early days of quantum computing being somewhat like the early days of classical computing. You know, you had to try different techniques, and there were vacuum tubes, and that was a step. And that we don't use vacuum tubes now. So do you imagine the future quantum computers will perhaps use elements of what we've seen before, but perhaps things we haven't even investigated yet?
Yes. Suddenly we might stumble into a better physical implementation of quantum information, which is more robust to noise. In fact, I would say the biggest challenge that we see today trying to build quantum computers is the noise and quantum decoherence. And that's why quantum error correction is really important. That's the main technique that we have right now to have the idea of scaling up. But I can see this changing. Like there's this beautiful quote from Popular Mechanics, 1949, saying the ENIAC, which was one of the first classical computer, the ENIAC had 15,000 vacuum tube and weighed 30 tons. And we could imagine the future having computers which would weigh only a ton and have 1,000 vacuum tubes.
Dare to dream.
That's it. And if this would have been a scientific paper, you would say, okay, they tried to be careful, but that was popular mechanics. You would give them a license to kind of dream and kind of having that wide imagination. So it does show that suddenly and transistors, in fact, were just appearing in labs, totally disconnected, and people didn't think they would be used for computers at the time, appeared, and this changed things completely. Mm-hmm. Maybe the implementation that we have today of quantum computers are the ENIAC type. And suddenly we could find some form of artificial particle in some material science. And there are suggestions about this called topological quantum computers with anyons. Maybe these things, if we can make them in the lab and be able to control them, they would become naturally robust to noise and give us a chance to scale up. But again, this is part of the dream, and we hope that we see these things. In fact, it would be very neat to discover something that kind of suddenly makes it a lot easier, because today, building quantum computers is very hard.
Still very, very hard.
Very, very hard.
Well, on the topic of dreaming and the future, I think this would be a good place to play for you a question that was sent in by a student. So this one is from Mohammed Habat Allah, and he's a PhD student at the University of Waterloo and the Vector Institute in Toronto.
Thank you for taking my question. So I'm a physics student at the University of Waterloo. My question is related to quantum computing. So as we all know, there is a lot of research all over the world for the purpose of building a useful quantum computer. So my question is, what do we need to build a quantum computer that is useful to real-world applications? And what do we need to do to reach the point where quantum computers can outperform classical computers? Thank you.
So that's a very good question, and in a bunch of different parts. So I'll start by the last part. So what do we need to have a quantum computer which is more powerful than classical computers that we have around? And it turns out we're pretty much there. That we have quantum computer prototypes around the world, one at Google, one at IBM, that are big enough to do a computation which classical computers are kind of have incredible difficulty to solve. So we're just on the border. And a little bit discussion if we're there and there, but to me, it doesn't really matter. We are kind of at that border. And so the challenge there is that these problems that these quantum computers are solving are not that interesting for day-to-day application. So, but I think it's quite a milestone. If I compare this to 10 years or 20 years ago, then to arrive there, again, 15 years ago, there were people who were saying that we will never be able to build a quantum computer. And here we have a prototype today. We have controlled these quantum bits well enough to do a computation that a classical computer kind of can barely do. Or to turn this into a device which is very useful for practical application, then we have to scale the number of these quantum bits. And as we scale the number of quantum bits, it's very hard to make them more and more precise. So if you have an error rate per operation, which is P, then as you have n of these qubits, if the error per qubit is P, if you have them, the error rate goes like n times P. Mm-hmm. So if you have 100 qubits, it's 100 times higher. And if you have 10,000 qubits, it's 10,000 higher. So this tells us that we won't be able to compute in a way which is fault tolerant or kind of to have confidence in the result if we don't have a mechanism to take care of these errors. And again, that's what quantum error correction tells us, that we can bring this NP to some constant value and compute. And so we need to be able to have a device with quantum error correction. At least the focus is there. We don't know how to do this without quantum error correction. And so we need to do this. And that will probably take another 10 years.
Mm.
That's roughly the things. Hopefully I'm wrong and it's in 3 years. And I hope that I'm not wrong, that it'll be in 50 years. But this consensus and some people in industry claim that probably by the end of this decade, roughly 10 years, we should have these devices. And we'll need many thousands of qubits to do this. So the noise has to be thought carefully. And how do we control these qubits also? Like right now, we do this brute force. We send one little wire for every of the qubits that we have. But if we have 1 million, and how do we kind of link all of this and make all these kind of wires that goes into all of the qubits? It's not totally clear right now. There's a different architecture. So I saw something from IBM Open Day last week about making a sandwich of qubits and having wires to come to them kind of different ways, which I thought fascinating. And although I've seen kind of people talking about architecture, they had very concrete plans to do this. So there will be progress that will happen. So that's why the field is incredibly exciting. There's new things every day in this field happening.
This field wasn't the original field that you got into when you started studying science, right? It was, you were more interested in the universe in its largest scales, right? You were more into cosmology?
Yes, I was in cosmology, but a small branch of cosmology called quantum cosmology. Okay. So what is quantum cosmology? So the universe is very, very big. And I've told you a few minutes ago that quantum mechanics is what describes the world when it is very, very small. So these things seem to be, at first sight, contradictory in terms. Mm-hmm. But the universe is very large, but it is expanding. And so instead of thinking about the future, if you look at the past, it means that the universe was a little smaller yesterday, even smaller the day before, even smaller before. And then we can trace back using Einstein's theory of relativity. We can trace back and ask the question, how long does it take before the universe is kind of small to a point? And it's roughly about 13 billion years. And at that point, quantum effects should come out. Mm-hmm. So what I was studying is, how do we use quantum mechanics to describe the beginning of the universe? Mm-hmm. So I work in Cambridge with Professor Stephen Hawking, and on a proposal that he had called the Hartle-Hawking, or the no boundary proposal. So I was trying to understand how this proposal was kind of fitting what we observe in the universe, and does it make sense, and try to interpret this wave function. The wave function is a mathematical tool which describes everything we can learn from the quantum system that it represents. I was trying to understand how it interprets. And in usual quantum mechanics in the lab, we interpret the wave function as it gives us the probability for something to happen. And we show that we have the right wave function by repeating the experiments many, many times. And then you get the probability distribution of different events. And this probability kind of maps with the wave function. The problem with this, the universe, we cannot kind of having many of these experiments. We have only one of them. Mm-hmm. So how do we use this wave function to make prediction? And it turns out that decoherence is a tool, or quantum decoherence is a tool to turn this wave function into probability of classical events. Mm-hmm. So I knew this quite well, and this is part that I learned while I went to Vancouver with Bill Unruh. And it turns out that when I was at Los Alamos, my mentor, Wojciech Zurek, was probably the best known person in the world working in quantum decoherence. And when I went to this talk about quantum computers, then I could put the two things together. Kind of quantum decoherence was an asset to interpret the wave function of the universe, but an impediment to build quantum computers. But again, it's the same mathematics. Right. So I jumped from one to the other. And at that time, I thought, I'll work a little bit on quantum computers for a few weeks, and then I'll come back to the fundamental issues of quantum cosmology and work with the universe. But I got stuck on quantum computers for a while.
And actually, one of your current students sent us a question about this time in your career. So maybe we can play that one.
Hi, Raymond. This is Matt Duchesne, one of your students at IQC and Perimeter. How did your advisor, Stephen Hawking, react to your career pivot? Did you two still discuss science and quantum gravity topics after you transitioned to quantum computing?
Again, a very, very good question. And so I had the chance after finish my PhD, I would bump into Stephen or kind of go to Cambridge from time to time. And Stephen has always been driven by curiosity. And this is something which has kind of always puzzled me. When I was a student, he was already incurably disabled. Mm-hmm. So he couldn't do pretty much anything by himself. When I started as a grad student, he could speak then, and he could move a joystick on his wheelchair to move around, but he would not be able to put his leg, or he was barely able to put his leg back on his little stalls of his wheelchair by himself. Mm-hmm. But he couldn't feed himself, couldn't go to the bathroom by himself, so he couldn't kind of lift himself in his wheelchair. So incredibly disabled. But Stephen was curious and he knew an incredible amount of things. I always wonder, how did he learn all of this? If he had to read a book, like today we read in the internet, we just kind of move from pages to pages or read a book. He couldn't turn the page by himself of a book. So he had to have somebody all the time doing this. And so, but despite all of this, he had incredible knowledge on a broad level and curious about so many things. So certainly when he came to Waterloo, and Stephen did come to Waterloo many times in the last 10 years before he passed away, he was always curious to learn different things. And I remember at some point I asked him, are you interested to come and visit the labs? He's a theoretical physicist, so I was not totally sure if that would interest him. And he was really keen. He said, oh yes, absolutely. And then I learned that while he was here, he had gone to Snow Lab in Sudbury. This is a lab where people have measured the mass of the neutrino for the work that they got. Professor McDonald got a Nobel Prize for the work that they have done this. And it turns out that the lab to measure this is in a mine. And the mine is still active, but you can go and visit it. You can go and visit and you go in this kind of elevator. You go down, I think it's 2 miles down the ground. Mm-hmm. And then it becomes really hot. You go down there with the miners. And as you get out of the elevator, the miners goes to the right and kind of the scientist goes to the left. And then you walk for about half a kilometer down there. And then you arrive to a place which is a clean room. So incredibly clean part. So it's all closed off, sealed off. You have to get a shower before going to the other side. So everybody the men and women get on 2 different parts, all stripped off, go to the showers, go and get dressed, and then go and observe things. By the way, if you have never seen this lab and you have a chance in Sudbury, just go. It's totally amazing place. So I hear that Stephen was interested and he went. And I said, how was it? And he said, the elevator was great. It was like free fall. So for somebody who was the master of gravity to be in an elevator for that long and felt like free fall, he thought it was absolutely fantastic. So we went to visit there. We came back here, and during the week came and visited the lab. And at every lab, he had some really interesting questions. And you know that he knew some pieces of all the different parts we were talking about, which totally amazed me. I said, where does he get all that knowledge? But it was very interesting.
I remember when he visited IQC a number of years ago, we had a gift made for him that you gave to him, and it was a wooden boomerang. Can you explain why we chose a boomerang as a gift to Stephen Hawking?
So that comes back to the first project when I was a graduate student of Stephen, which was to try to prove that the wave function that bears his name, the Hartle-Hawking wave function, showed that the arrow of time would reverse at the time of maximum expansion. So the universe has started very small, we have the Big Bang, which is like an explosion. The time people thought that the universe would reach a time of maximum expansion and recollapse. At the beginning of the universe and at the end of these universes, there are something called singularities, places where physical quantities would go to infinity, which essentially tells you that the theory by itself breaks down, a place where something different will happen. And so classical relativity, Einstein's theory of gravity, would break down there and should be replaced by something else. And Stephen had been working that quantum gravity would be what would replace and smooth out these singularities in some ways. Mm-hmm. And because he wanted his wave function that he had picked up, his quantum wave function was smoothing out the singularity at the beginning, he thought that it would smooth it out also at the end. But today we see entropy or disorder to increase as we go. So at some point, this would have to reverse and come back so that it goes to a smooth thing. So that was my first project. And I had to show this. So he had the idea, and then you had to show that the math agrees with the idea. So we've talked about this a little bit before, that kind of, it's great to have ideas. Some are right, some are wrong. And usually really smart people, clever people like Stephen get them all right straight away. And I started to work on the math of it, and I couldn't make it work. I just couldn't make it work. And I would go and see Stephen once a week and show him my progress, and he would always pick apart some of my argument or my comments or ask me, have you checked this carefully? Well, I was a grad student just starting, so I had not checked everything. And I'm sure other grad students would understand very well that kind of you go and see your supervisor, you think you have everything neatly done, but suddenly, there are little pieces under the carpet there that kind of you had assumed. And so Stephen would pick at me all the time. Fortunately, after a couple of months, 3 or 4 months, one of his ex-postdoc, Don Page, came. And he asked me what I was working on, and I told him, and I said, I just cannot make it work. And he said to me, oh, it's interesting because I've been thinking about this. And also I believe that it's not going to work. So then I felt reassured because for the last kind of 6 months, I was trying to I thought that I was the one who was wrong. And so Don, who was a little bit older than me, said, Stephen will never agree if we just go brute force and tell him he is wrong. What we have to do is slowly putting the pieces together and build our argument and add one more piece to the other, which each of these little pieces don't say that the arrow of time will not reverse, but kind of all together will kind of bring. And so we did this. And after about 2 months of arguing, that both of us kind of were putting, Stephen came and said, it's never going to work. And then suddenly he said, oh, yeah.
Right.
And so when I finished my PhD, Stephen gave me a copy of his book, A Brief Restaurant, and with a little quotation at the beginning, to Raymond, who showed me that the arrow of time was not a boomerang. Best, Stephen Hawking. Mm-hmm. So when he came to visit here, it was kind of 20 years later, then I gave him a boomerang of all this. And then he had a big smile on his face. And interestingly enough, in the following year, there was a documentary on him that I was watching at some point. And it was at this house. And I could see in the background, the boomerang was there on the wall, put there. So this is the story of the boomerang.
Wonderful.
Well, this actually leads into one more question that we got. And this one was from Nayeli Rodriguez Briones, she's a postdoc at the University of California, Berkeley, but she did her PhD doing some work with you. And so she actually wanted to know what your fondest memory is with Stephen Hawking. And you've shared a few now, but I'm curious, what's the fondest when you look back on all those times?
Oh, that is a really good. There was many fond moments. I think maybe one piece that surprised me about Stephen is, scientists, some of them are very stubborn. Some of them kind of have ideas and they think that all their ideas are right. One thing which really amazed me with Stephen is when suddenly he realized that he had made a mistake on this proposal on the arrow of time, he totally turned around and realized and said explicitly in conference and talked in his book that he had made a mistake and realized that things were going differently. And he gave me a lot of credit for it. And kind of suddenly, I thought he was incredibly generous. And so that was a part of Stephen that I didn't know that much before. Like he was my boss and somebody incredibly smart person. I was a small graduate student kind of stumbling on this problem.
I can imagine the intimidation factor of telling Stephen Hawking, I think you're wrong about that.
Yeah, I must admit that I never said it explicitly that way. I would say, I would go to the blackboard and say, I don't see how this can work, or I don't see this working. And then you would go, I would tell them I've done this and this, I do this calculation. And if I look at this, I get this result. And so I'm not getting what you're thinking. Yeah. So a little bit different than saying, you're totally wrong, Stephen. Another thing of Stephen, which is amazing, is his sense of humor. He liked to tease people, and this happened often between him and me and the staff around, kind of would play tricks on each other and throw things to each other at different places. He would have a good laugh, and I was not very shy. And this, I don't know why is that, but many people who arrive next to Stephen totally freeze and kind of, he was very, very disabled. And his voice was distorted when I started to talk with him. When I started my PhD, after that, he had a computer. So people would kind of often, if I would be helping Stephen, they would ask questions to me instead of Stephen because they don't know a kind of reaction. Maybe I can thank my mother who was very hands-on and not be shy and always telling us, the kids, to help whenever help was needed. So I would help Stephen, and something I would say to Stephen, kind of, I just don't know what to do now, kind of trying to help him when things were not going right. Stephen's sense of humor comes out in different ways that quite often people don't notice. And once you notice it, he likes to joke, he likes to tease people, he likes to kind of have fun. And that's one part that I really was impressed of him, of somebody who's incredibly disabled. Like, I've rarely seen people as disabled in my life who can still function and do extraordinary things. Kind of being a worldwide scientist, travelers, nearly a rock star in many ways, but at the same time being incredibly, incredibly disabled. And this kind of, this is something that really impacted me, saying, if you have really want to do something, then things are possible. Like, don't let yourself kind of pity yourself and stumble onto things because of hurdles of things going.
That actually leads into my next question. One of the reasons we're so delighted to have you here today is that a doctor told you some years ago there was no guarantee that you would be anywhere today. So you had a prognosis of cancer that came out of the blue. Can you tell us what that was like for you?
Yes, 5.5 years ago, I was diagnosed with lung cancer, stage 3. So people who know about this knows that prognostics are not that, or were not that great at the time. So I was told that I had about 20% chance of surviving 5 years. And I was, except for the lung cancer, perfectly healthy. I like to do outdoor stuff. I like to go on bicycle. In fact, while I was being diagnosed, I went on my bike to a little cottage that we have on the way to Owen Sound, not very far from here, about 125 kilometers. I could do this. So I didn't feel really that it was that impacted me kind of that much, but the doctor told me the chances are very slim to go through. And that only made me change a little bit, kind of my view of the future. So it turns out that I had been director of the Institute for Quantum Computing for pretty much 15 years. And I had told the Institute that I was not going to ask for another mandate. So I could just kind of quickly wrap up. And I thanks my colleague, in particular, Kevin Resch, to have taken over at the Institute at that time. And I had to go through chemo surgery, radiation, and all that stuff, and more chemo. And suddenly things seems to have kind of picked up, and things went okay. I had a recurrence about 3 years ago, but it turns out that the particular cancer that I have is one particular piece of my DNA that's changed, and there's targeted therapies. It's a mutation of the DNA, which is known, and there's a drug that kind of came to the market 5 or 6 years ago. And that particular drug kind of stops the cancer to go, and it's been incredibly good. So thank you for medical researchers, people who design drugs, and thank you for the company who makes this drug, kind of, that I'm still alive today. And here I am, and things look good.
You mentioned last time we spoke that there's actually a note on your file at the Regional Cancer Center saying, no, this guy's a physicist and he asks a lot of questions. Can you tell, were you asking questions about the machinery they were using for their diagnostics?
Yeah, in fact, when I went to add treatment, there was kind of 3 pieces of it. Surgery, that's kind of biology stuff, and this, I don't feel that much attraction to that kind of stuff. Then there's chemotherapy, chemistry, all these thinking stuff and kind of liquid things that again, I'm not too keen on this. I try to understand a little bit how it works, but kind of, it's not natural to me. Radiotherapy, that's radiation, that's electromagnetism. This, I can read about this. I can try to understand kind of how it works. So I started my treatment of radiotherapy here at the hospital in Waterloo. And I started to ask questions about the machine. And I was really curious to see kind of how it works. So I started to say, well, kind of, what is the frequency of the radiation that we have? And so the staff who were doing, I'm not totally sure, we're kind of ask, and they would come back and tell me this. So some of the question I would ask, they would come back and know the answer, kind of, how long does that process works and all this? How do you calibrate the machines? And that's one day I came and I said, well, do you have the instruction manual for the machine? I'd like to double check a few things. So they burst laughing, and he said, we have a medical physicist on staff at the hospital. Maybe we can set up an appointment with him. So his name is Ernest Jose. And so the next time I came, after my appointment, he was there waiting. And he said, apparently you're a curious man. And then he told me this. He said, apparently in your file, there's a note saying this guy is a physicist and ask a lot of questions.
Amazing. Did they ever give you that operations manual for the machine?
I didn't get it through the hospital. I got it through the internet somewhere. I kind of figured it out. And then interestingly, the medical physicist was giving a course on oncology and therapies at the university, which I didn't know about. And so I asked him if I could get in his course and kind of to just be a listener. To which he laughed and he says, if you want to, it's fine. So I joined the course, and I spend the kind of the rest of the term kind of at the back of the lecture room and asking questions from time to time. Try not to intimidate the students who are at the front, but quite often they had questions about what do patients feel when certain things happen, and kind of question that patient would have. And so there I could help them a little bit. So now I know how radiation theory. And I'm thinking that maybe there are ways that quantum technologies could kind of help them and kind of controlling, after all of this kind of comes down to controlling radiation. And in the NMR quantum computing that I do, we do control the radiation in certain ways to kind of reach certain goals. So I think some of these techniques can be applied there.
Amazing.
Well, you've sort of become interested in new fields a few times, right? You started out working in quantum cosmology, and then you became interested in quantum computing, and now you've acquired some knowledge about medical physics. But I think it must be very difficult when you try to start learning about a whole new field. There's so much vocabulary and maybe assumptions that people take for granted. Was it difficult to move into those new fields a couple of times?
Um, yes, there's definitely some hurdles, but I would say this is the price I'm paying for being curious. And it's a wonderful thing to be curious because it tells you that you're never bored. There's always some neat things that you can learn about, or kind of, I like to understand how things work. And that it be quantum computing, qubits, or quantum cosmology, or I have a Volkswagen van 1979, and it doesn't always kind of work perfectly, so that there are pieces I need to understand there. And while you do this, indeed, there's lingo that people are using. And that's probably most of the challenge, is to understand exactly what is the lingo that people do. And all different fields have different kind of assumption that people absorb without saying very explicitly. And these are the hard parts to kind of get over. But once you know that these are two hurdles, then you can pick the brains of other people. So I would say knowing this and not be shy about asking questions is something which is critical. And so I try to get my students not be shy. Personally, I'm a person who's shy in kind of a lecture room and all of this. But now that I know enough things, then that gives me kind of less shyness to be able to do this. And if my question is a little too naive, then I'll say, okay, I'm just new in that field. So what? And maybe being a little bit older, I become less shy of being seen. So quite often I see students worry about looking like fool of asking naive questions. But what I've learned is that sometimes the naive questions are the hardest one to answer, like the basic assumptions in fields of why do we do this way. It's kind of much harder to answer than a really specific technical tricks that people are using to get a solution of something. So asking things about assumption is, I think, very, very important, because once you know the assumption, and then you learn a bit of the mathematics, then it's straightforward to kind of move on.
You've mentioned in this conversation several times the power of curiosity. I remember you gave a talk, a TEDx talk about 10 years ago, and the very first word of it was curiosity. And that was a standalone sentence, curiosity. Is that something that's just you've had innately your whole life? Have you always been that way, or is that something you've developed over time?
That's a really good question.
I'm curious.
I think there's an innate part. I think there's an innate part that everybody has. And I think that it comes down to Darwin's principle that humans who are really curious can harness this curiosity to turn their life into something better. And I think that's the story of developing technologies. So you start with curiosity, and suddenly people like me, we're physicists, kind of trying to understand the world around us and try to ask questions about how does it work, and kind of why do we see what we see, and trying to build what we call theories. So theories, at first step, try to put together a bunch of data of observations and kind of link them in a consistent way. But the second step of the theories is something that allows us to make prediction of what's going to happen in the future. And then that's one way that in the scientific method that we prove that our theories are good, is that they have a predictive power and they agree with the future experiments that we're going to do. But also once you know how to predict things, you can learn how to control these physical phenomena that we have around. And once you can control these physical phenomena, you can make them do things that helps you and helps you to survive. And that's what we call technologies. And I think the cycle of going from curiosity making theories, controlling, and then kind of developing these technologies have come again and again. And once you develop new technologies, interestingly, you can push your curiosity steps kind of ahead or further down or further up, depending on the scale that you're looking at, and trying to understand more physical phenomena and take that cycle going again and again and again. And so I think curiosity is something that everybody has. People use them in different degree, I would say. But I think everybody's curious. And that's what makes us drive and kind of ask interesting questions.
Ray, I could talk to you all day, and there have been times when we have chatted for hours, but we won't keep you any longer. Can you just share with us what your outlook is for the future and your research and your curiosity?
Well, I think you want to talk for a few more hours. Again, I said, I'm curious about different things. Now I have the luxury of not being director of any institute, so I have plenty of time to do things which, when I was director, I had to focus on developing this Institute for Quantum Computing, but now a lot of time to read things. And I get lost from day to day on kind of reading too many things. But definitely on the scientific part, I want to better understand how to control these quantum systems. But also, having been a director of an institute, I want to understand how do we really go from ideas and this curiosity to really develop technology. And how do we do this in a Canadian context, for example? How do we what are the pieces that we're doing very well in Canada and what are the pieces which are missing? That's another part. And if we go to kind of larger and larger scales, one day I'll come back to quantum cosmology and trying to understand how the universe works. And between the small world and the large scale of the universe, there's plenty of things kind of to push my curiosity in different directions.
Wonderful. Well, thank you so much for spending the time with us today.
You're welcome. Great pleasure.